Okay, have a look at, say, page 31. Okay, so page 31, this one is June 18 P41. So have a look at that. Let's have a look at June 18 P41. Sometimes they give you a question that looks like this. This is the one. Okay, have a look at question 2. So you look at page 31, they mentioned that a plate is made to vibrate vertically by means of an oscillator as shown. Some sand is sprinkled onto the plate, and then the variation with displacement y of the acceleration of the sand on the plate is as shown here. Okay, this is for the sand right over here. They're giving you the graph of acceleration versus displacement shown like this. So in our current case, they ask you to use the figure to show how it can be deduced that the sand is undergoing simple harmonic motion. So this is your standard vanilla acceleration versus displacement graph. So you can actually see from this graph that this object is undergoing simple harmonic motion. So that time I told you A is negative omega square x. If you plot a graph of, say, A versus x, after comparing it to y equals to mx plus c, you should get, number one, you should get a straight line graph passing through origin with negative gradient. Okay, so from the equation A equals to negative omega square x compared to y equals to mx plus c, if you were to try and plot out the acceleration versus displacement graph, it will look like this. Okay, so it will be simple harmonic motion based on two things. If it's a straight line graph through origin, this means A is proportional to x. If it has negative gradient, this means A and x are always in opposite direction. Okay, so you're trying to do the same deduction here for your given graph to show that it's actually simple harmonic motion. So here you are basically following the same points. A straight line through origin indicates acceleration is directly proportional to displacement. And then a negative gradient indicates acceleration and displacement are in opposite directions. Okay. This is something we've done before. Then calculate the frequency of oscillation of the sand. So for your particular case, again, this one is something that I also kind of did mention before. If you compare your equation A is equals to negative omega square x with y equals to mx plus c, you will see that your gradient is actually negative omega square. So here, gradient is negative omega square. Then from here, they want the frequency, right? So gradient is actually negative 2 pi f square. So you find your frequency and your gradient from the graph, and then after that you equate it to 2 pi f. That is what is being shown here, like this. Okay, this is one part. This is using gradient. But I also did mention to you that you can use single point substitution, which is not shown in my working here. You find a pair of A and X from graph, then substitute into A equals to negative omega square x. Okay, this is another method that you can also use. Find a pair of A and X from the graph, and then substitute into A equals to negative omega square x. And just make sure that this one, eventually you make it into A negative 2 pi f square. Okay, wait, make sure it becomes 2 pi f square x. Okay, because you want to find f in the first place. Right? So you do the second method, it's also fine. Okay, not necessarily you always need to use gradient. All right. Now B is the one that's a bit different than the rest. This is the one I want to discuss with you. Now the amplitude oscillation of the plate is gradually increased beyond 8 millimeter. The frequency is constant. At what amplitude the sand is seen to lose contact with the plate. For the plate, when the sand first loses contact with the plate, state the position of the plate and then calculate the amplitude of oscillation. Okay, so in your current case here, you have some sand that is actually resting on top of a plate. So this is your plate here, like this. Now your plate and your sand are considered to be two separate bodies. They can be considered as two separate bodies. Now if you imagine that when the sand is actually not in contact with the plate, the sand actually has an acceleration equals to g, because then the only force acting on the sand is just the weight. Okay, so once the sand is no longer in contact with the plate, it should by right just move down with an acceleration of g. Okay, then your plate itself would have its own separate acceleration. Let's call this A of your plate, which depends on your displacement from equilibrium. So say for example, I write here the position of your equilibrium being somewhere around here. Okay, so let's just consider this as the position of your equilibrium. So at this point here, once my plate is on top of the equilibrium position, my acceleration of the plate ought to be towards the equilibrium position, and it depends on x, because A is equals to negative omega square x. From here, you can actually see that A is directly proportional to x. The further away I go from the equilibrium position, the bigger my acceleration. Okay. Then for the sand, let me just rewrite it. I mentioned to you that the acceleration is equals to g, right? So let's just call this acceleration of sand equals to g. All right. So this is the case that you're looking at right now. This is, for example, when your plate is on top of the equilibrium position and your sand starts to lose contact with the plate. So the sand will have an acceleration equals to g. The plate will have its own acceleration, which depends on x. So what happens then, if I mention a few cases to you, if your acceleration of your plate is less than g, what could then happen is this. For example, your plate right now is having an acceleration of, say, maybe 3 meters per second squared, but your sand is having an acceleration equals to g. Now you just look at it like this. Because your acceleration of the plate is less than the acceleration of g, this will tell you that the sand moves faster than plate. So therefore, it will remain in contact with the plate. Okay, so this one should be quite easy to understand, because sand now moves faster compared to the plate. It obviously will hit the plate first. It cannot be a case where it's lost contact with the plate. Okay, so this is the first case. Now, what about an opposite case then? If I tell you that the acceleration of your plate is more than g, you again now have something similar. This is your plate, whose acceleration now is probably 15 meters per second. So this is acceleration of your plate being 15 meters per second now. And then after that, your sand is right over here, where the acceleration remains at g. So here, because my plate is having an acceleration of 15 meters per second square, whereas my sand is only having an acceleration equals to g, this means that the plate moves faster than the sand. So therefore, the sand will lose contact with the plate. Therefore, sand loses contact with the plate. Okay, this one we will say that sand loses contact with the plate. Okay, so this is two of the extreme cases you can consider first. When your plate acceleration is less than g, sand will remain in contact with the plate. But when your acceleration of your plate is more than g, your sand will lose contact with the plate. Okay, so what about the case where you want to say the plate just starts to lose contact with the plate, the point where the sand just starts to lose contact with the plate? So if you're talking about the point where the sand starts to lose contact with the plate, it ought to be where acceleration of the plate equals to g itself. So if you consider this third case, where A of plate is equals to g, so in my case, you will get a case like this, where A of sand equals to g, and then the A of your plate is now equals to g itself. So when you have this case here where the acceleration of the plate is just equals to the gravitational acceleration g, you can say that the plate, sorry, the sand is at the point or starts to lose contact. It starts to lose contact with the plate. Okay, so that's what we can understand here. Because you see, when you look at the question mentioned this. Amplitude of oscillation of the plate is gradually increased beyond 8 millimeter. The frequency is constant. And then at one amplitude, the sand is seen to lose contact with the plate. So for the plate, when the sand first loses contact with the plate, state the position of the plate. You see, there's a part here that you need to kind of single out first. They say here that your amplitude is actually being gradually increased beyond a certain value. And then after that, they say that when your amplitude is being increased, there will be one particular point where you see your sand start to lose contact. So they are interested in the point where the sand first loses contact with the plate. Okay. So here, when they ask you to state the position of the plate where the sand starts to lose contact with the plate, the more exact answer is actually maximum displacement outwards. This is actually talking to you about the amplitude position above equilibrium. Okay, it is at the amplitude position above equilibrium that your sand starts to lose contact with the plate. Now, the other two answers here where they say is above equilibrium position or above resting position, this is a more general position for where the sand starts to lose contact with the plate. But the exact position, if they want the answer to be even more specific, is actually at the amplitude position above equilibrium. or maximum displacement upwards. Okay, now you may be wondering, why is it at the amplitude position? It's because of a few things to consider. Let me just write it somewhere here. I'll probably write it in green maybe. Okay, so why do we say it's at the amplitude position is because of this. Number one, because we know that A is negative omega square x, therefore A is proportional to x. This means that for any oscillation, for any given oscillation, the acceleration is always maximum at the maximum displacement position. The acceleration is always max at maximum displacement from equilibrium. In other words, at amplitude lah. This is what I just wanted to say. Okay. So you consider the case first that acceleration being proportional to displacement, when you have any given oscillation, if you're interested in this displacement, if you're interested in this acceleration, the acceleration would always be maximum at the maximum displacement from equilibrium. In other words, at your amplitude position. Okay, so that's fact number one to take note of. Okay, then fact number two that you can also kind of see from here is this. Now, as if you look at the question said your amplitude is gradually increased, right, from beyond 8 millimeter. In your current question just now, before this, they told you that the amplitude of oscillation was 8 millimeter. Your sand hasn't lost contact with the plate yet. But now they are gradually increasing the amplitude to the point that your sand starts to lose contact with the plate. So here when they say as amplitude is gradually increased, as amplitude is gradually increased, A of the plate, the acceleration of the plate will start to reach G at amplitude position first. Okay, so this one should make sense now. All right, it should make some sense to you now, because the question is saying that your amplitude is being gradually increased here. So when your amplitude is being gradually increased, the acceleration of your plate will start to reach G at the amplitude position first. So this one, so far so good with this? Because you see, you want your sand to start lose contact with the plate, the acceleration of the plate must be at G in the first place. But here, specific to the question, you're trying to increase the amplitude from a low value to some sort of high value. You're interested at the amplitude where you start to see the sand lose contact. So where the plate starts to have an acceleration equals to G first, it will be at the amplitude position first. So far, so good with that?
Yeah.
Okay. All right. So from here, we only know one thing. Your sand will start to lose contact at amplitude position. But why must it be at the amplitude position above equilibrium? Why can't it be the amplitude position below equilibrium? Okay, so this is another thing to kind of take note of. This one is another fact I'll write. This one I'll probably write it over here. So you see, for sand to lose contact with plate, there are two conditions. The first one is that acceleration of the plate must be more than or equals to G, and then the plate must be moving downwards. Okay. Just now here, when I explained to you that the acceleration of the plate must be equals to G before your sand can start to lose contact with the plate, there's actually another condition that's indirectly inferred here. That one being that your plate must actually be moving downwards in the first place. Okay, so there's two conditions here. Acceleration of the plate must be more than or equals to G, and plate must be moving downwards. Okay, so now you try to relate to what I say in point number 2. I say that your acceleration of your plate will only reach G at the amplitude position, but why can't it be the amplitude position below equilibrium? Why must it be the amplitude position above equilibrium? Now it's because of the fact that, you see, when you are at top amplitude position, when your plate reaches the top amplitude position, let's just say it's right over here now, this is say the top amplitude. In the next instant of time, once your plate has reached the top amplitude position, it's correct to say that your motion will be downwards, right? Because you already reached all the way to the top at the amplitude, the next subsequent motion would obviously be downwards, okay? So you see, at the top amplitude, your plate starts to move down. But if you're talking about a case where your plate is at the bottom amplitude position, let me just draw another diagram here like this. Say this one now is your bottom amplitude position. This is your bottom amplitude position. Yeah, you reach bottom amplitude position here. If you consider the next instant of time where the plate will move, the plate will actually start to move upwards. It cannot move any more downwards because it's already reached the amplitude position. That's as far downwards as it can go. So the next instant of time, it must be moving upwards. So here, the next thing you can probably say is that at bottom amplitude position, the plate starts to move up. Okay, so I know that at these two positions, the acceleration of the plate is equals to G. Will start to be equal to G or more than equals to G. Okay, at these two positions, at the top and bottom amplitude position, my acceleration of the plate will start to be equal to or more than G. But there's another condition that I needed to have, that one being that the plate must be moving downwards. So between the top and bottom position, top and bottom amplitude, sorry, which one is actually moving downwards? It's actually supposed to be only this one, isn't it? So from here, I can say that, therefore, a sand loses contact with plate at top amplitude position. Okay, this is the point where you start to lose. Okay, the keyword here for your question was they are interested in finding out the point where your sand first loses contact with the plate when your amplitude of oscillation is gradually increased. Okay, so you can actually say that it will start to lose contact at the top amplitude position first. Okay, this is the exact point where you start to lose position, which is actually what the marking scheme wrote here lah, at maximum displacement outwards. The other two, above equilibrium position and above rest, is actually a more general position of it. It's a general answer, but the more specific one is at the top amplitude position. Okay, so far so good with this. Why B1 is worded like that?
So for sand to lose contact with plate, plate must be moving downwards because we are looking at the acceleration, is it?
Okay, you consider this now. Why must it be moving downwards in the first place? Is because you see each. Let me just draw it here in a separate color so you can see the difference. You consider this, if my sand is having an acceleration equals to g, my sand is having acceleration equals to g, and my motion is downwards for my sand. This is my motion downwards for the sand. And then after that, I say that my plate is like this. Okay. And it is moving outwards. And I tell you that my acceleration of my plate is also equals to g. In such a case, is it even possible for the sand to lose contact with the plate? No
No.
doubt that both of them have the same value of acceleration, but both of them are actually moving towards each other. So it will not lose contact at all because one of them is moving towards the direction of the other. So it cannot be in a case where the plate is moving upwards. It must be a case where the plate is moving downwards. Only then can it start to lose contact.
Okay.
Okay.
Yeah.
So that's why here you specifically want to find the point where the plate is starting to move downwards, where the acceleration is equals to g. Only then can your plate start. So only then can your sand start to lose contact with the plate. Okay, so that's why here I kind of highlighted to you. You must have these two conditions. Acceleration of the plate must be more than g itself, and the plate must be moving downwards. Okay.
Yeah.
So that one should be okay, right? Because sometimes people may also ask. This one is a bit further from what we discussed, because sometimes some people may ask, if you are below equilibrium position, if this is your sand whose acceleration is equals to g, isn't it also possible for your sand to lose contact with your plate when it's moving downwards and your acceleration is equal to, and your acceleration is more than g itself here? Let me just indicate for you the bottom amplitude position first. Let's just say that this one here is your bottom amplitude position. Okay, the blue colored line here is your bottom amplitude position. Your plate now is right over here. Because sometimes people will also say, when you are below the equilibrium position and your plate is moving downwards, if its acceleration is more than g, wouldn't your sand also still lose contact with the plate? Yes, that is correct. Okay, your sand will start to lose contact with the plate below the equilibrium position even before you reach the amplitude position in this case. But the question is not asking you that. The question is asking you for a very specific case. The point where your plate starts to lose contact, the point where your sand starts to lose contact with the plate as your amplitude is gradually increased. So you're actually starting from a very low value where your sand hasn't lost contact with the plate. So from there, you gradually increase until you start to see the sand start to lose contact with the plate. So in such a case, it will be at the maximum amplitude position upwards. Okay. Now, if you start to go and increase your amplitude even further, such that your acceleration is even larger, no doubt you have a case that looks like this now. Before you even reach the bottom amplitude position as your plate is moving down, you could have a case where your plate acceleration is more than g itself. So your sand could also lose contact below the equilibrium position. So because some students, if they think too much about it, they could also say that, why must it be above equilibrium? It could also be below equilibrium. But that is true, but then you need to answer specific to the question now. They say, the point where it first loses contact when your amplitude is gradually increased. When your amplitude is gradually increased, it means to say your acceleration of the plate is gradually increased. So you are trying to increase the acceleration of the plate to the point that is equals to g first. Then after that, you want to see the point where your plate starts to lose contact. Okay. So far so good. Yeah, this is the explanation for this. No? It seems pretty simple, but somehow when people think into it, it becomes a bit more confusing. All right. Now, with this understanding here, you would probably understand why is it that 2, we ask you to calculate the amplitude of oscillation when the sand starts to lose contact with the plate. So here we already know that the sand will start to leave the plate when acceleration is equal to 0. Then you use A equals to negative omega square x, or rather you use A is omega square y naught to find the answer here. You can just ignore the negative because we're just interested in the magnitude. And then after that, your x naught here is replaced with y naught, because you're following the question. All right. Okay, so this one is all right.